I'm glad to have the opportunity to share our team's work on this meeting. I have been focused on the drag reduction area over 20 years. My presentation today is a novel drag reduction techniques and energy efficiency for HVAC systems. The outline of my presentation is as follows. I will introduce the drag reduction of HVAC system from the following 4 parts. Let's start from the first part, background. The resistance of the HVAC piping system is pertinent to all kinds of buildings, including the residential buildings and the industrial production buildings. Okay. For example, the building energy consumption will occupy the total. The building energy consumption will occupy the 20% of total energy consumption in China. However, the resistance of the HVAC systems will occupy over 30% of the total building energy consumption. The drag reduction has a long way to go. The electrical journey of our 1,000 miles starts with a single step. Look, this picture shows the intricate the HVAC dust maze. At present, as I said before, the building energy consumption in China accounts for more than 20% of the total energy consumption, of which the HVAC, to heating, ventilation, and air conditioning system accounts for 50% of the building energy consumption. There are many factors to affect the resistance of the HVAC dust, such as improper or unreasonable manufacture, improper design, improper installation and operation. It's of a great practical significance to optimize the local components of the HVAC, the components to reduce the drag resistance and improve energy efficiency. Through the optimization of the local components for HVAC system, we can reduce the drag resistance remarkably. There are different ways to reduce local resistance coefficients for HVAC system, including the drag reduction use the turn wing, drag reduction use the rectifier, the drag reduction use the modified arc surface, and so on. Drag reduction use the turn wing. The principle of the drag reduction use the turn wing is that a lot of wattage can be decomposed into small ones through the soldering of the additional solid wall toward the fluid vortex, which will reduce fluid resistance in the local components. Setting the turning wings and the separation point of the vortex can effectively weaken the range area of the vortex. Arc surface the drag reduction is to change the radius of the curvature cross-sectional area through the deformation of the local components of the pipe and the pressure gradient springs. And the pressure gradient springs are weakened remarkably. The vortex springs is reduced to achieve the purpose of drag reduction. Please pay attention if the radius coverage of the eyeball is increased too much. The large components will occupy the more space. Next, the part 2 is about drag reduction theory and technology. The two types of the drag resistance loss are friction loss and the local resistance. The actions of the local component resistance reduction is to lower the energy dissipation caused by the air vortex. Controlling the airflow vortex, we can reduce the drag resistance remarkably and improve energy efficiency. First, let's take a look at the influence of the air velocity or the local resistance loss of the inner rectangular duct air ball. Then the influence of the air temperature on the local resistance loss of the inner rectangular duct air ball is shown on our right. Okay. Please pay attention. The air velocity in the duct and in HVAC system, in heating, ventilation, and air conditioning system, is generally 3 to 15 meters per second, and the air temperature normally is the 15 to 30 Celsius degree. And our team started the drag reduction for many years, about 20 years. Okay, here is the effect of the rectangular duct width to height ratio on the resistance loss of air ball. This picture shows the part of our current our team's result. Okay. As for the influence of the radius of curvature of a rectangular duct air ball, the resistance loss of the air ball, we did some simulations and experimental research based on the air ball models with a different radius of curvature. This picture shows the influence of uneven flow in a duct, okay, internal flow on the loss of the rectangular duct air ball. Okay, please pay attention to the picture in the middle. Okay, we can find the local resistance component is quite different. The slide next two slides shows our team's research, the results on multiple air ball. The one air ball will combined with another air ball. With our research on multiple air balls, in fact, in a rectangular ducts, and the influence of cardboard air balls on airflows. Okay, and this slide. We have optimized the curve of the air balls, and we can have optimized the arc surface of the air balls. Okay, the first is the central axis. The central axis is essentially changed the overall of the air ball of the three arcs. The table illustrates the resistance reduction effects of a typical transformation schemes for different central axes. Okay, from this slide, you can see at the outer of the arc, the core of the outer arc transformation is influenced by the transformation of the arc. Okay, the picture demonstrates the reconstruction of the plane. That means we can change the traditional arcs into the new arcs. Okay, then through the change the shape of the airballs, we can reduce the resistance remarkably. Okay, this slide is about the inner arc. The core of the inner arc transformation, the core of the inner arc is changed. Okay, so we can remarkably to reduce the negative pressure area of the vortex. the comprehensively, these are both the inner and the outer arc. Okay, we can consider the comprehensively the both inner and the outer arc. Okay, the numerical simulation is carried out, and the experimental test also is also performed. Okay, by the coupling of the different schemes of the inner arc and the outer arc for the airballs. Okay, we can get the better the drag reduction. Look on our look there is a table on our right. Okay, you know the best drag reduction rate is about 9.21%. Okay, the expansion optimization of the airballs is also proposed. It's also studied in our teams. The key points of the expansion optimization are suggest to extend the length, direction, and the shape of the outer arc and the inner arc. Okay. This picture is just shows, you know, the comparative study, correct? On our left is the traditional airballs. On our right is the current novel airballs. Okay, you can see for the traditional one there is a remarkable vortex. Okay, for the traditional airballs, which leads to high resistance, but on the right side of this picture, you can see the vortex is basically disappear. Then through the optimization of the different positions of the turning wings, the erection position, okay, we can get the equations to predict the inner arc. We can get the equations to predict the outer arc. Okay, this on our left and on our right, there's a short equations to predict the arc to predict the outer arc and predict the inner arc. Okay, for the airballs. Through the equation, we can get to optimize the airballs to reduce the resistance remarkably. Then here is we can optimize the airballs by inserting the different the wings. Okay, different train wings. Okay, we can find a different location, different shape. Okay, that have a different effects on the drag reduction. On our right, you can see the best drag reduction is a 4.18% for the airballs. This is a comparison of the total pressure loss and the increase or decrease ratio compared with the traditional airball drag reduction compared with the traditional airballs. Okay. On our left, you know, on our low, the left is the traditional airballs. On our low right is the standard airballs. Okay. On our left is the optimized. Okay. On our low left is the optimized airballs. On our right, okay, the low right is the traditional airballs. Okay. You can find the different shapes. Okay. Then you can different drag reduction rate. From this table, we can find the best result is the 9.21%, the drag reduction rate. The next two slides, okay, the 27 to 28, okay, shows a comparison of the total pressure loss and the increase or decrease ratio compared with the standard or traditional air balls. Okay. Okay, these kind of different T-junctions. Okay. On our left, the flow rate, the ratio is a constant. On our right, we can change the flow, the rate ratio. Okay, so we can find a different the drag reduction rate. Okay, this optimizes the position for the train weight in the T-junctions. Okay, here is a short novel drag reduction technology for the T-junctions. Okay, we can from our left, and in the middle, and on our right. Okay, to the short different components the drag reduction for the such as for the straight through, the direction, or for the branch the direction. Okay. Okay, in this slide, we can find the velocity field and the pressure field for the T-junctions. Okay. So we can compare the traditional ones and the optimized ones. Okay. We can find through the optimization of the T-junctions, the air velocity field and the pressure field are remarkably changed. There are different. Here is a short. The different 31. Here is a different T-junctions and the drag reduce the method. Okay. The first is on our left is the straight through, the straight through direction. Okay. On our right is the branch direction. Okay. We can find so the straight through bypass, branch bypass, and both. Okay, can be the drag reduction can be reduced. Okay, by the different shapes or different arcs surface. We have carried out the two-dimensional PRV test. Okay, this is a two-dimensional PRV test on the drag reduction for air balls or for the T-junctions. We try to find the exact air velocity and the pressure field. Okay, for the optimized T-junction or the traditional junction through the field. These are the details of the PRV experiments. Here this picture shows the results of the PRV, the test. Okay, with the CFD simulation, with or without the drag reduced. Okay. Okay, Father, the on our left, on the first line, is a velocity field of CFD simulation without drag reduction. Okay, and the low part is with the drag reduction reducer. Okay, this slide shows the influence of the branch pipe, the connection mode. Okay, different branch pipe connection mode that have a different effect on the resistance reduction. Okay, we can change the connection, the model between the branch and the main pipe, so we can reduce the vortex area and so to reduce the local resistance. Please have a look at the 5 pictures, the different connections. Okay, and the middle one is the perfect one. We recommend the middle one is used for the HVAC system. The drag reduction for airballs and the T.junction for the T.junction closed compound. That means the both airballs and the T.junction are closely compound, are closely installed. Okay, so they have some influence to each other. Okay, this picture shows the drag reduction for airballs and the T.junction closed report. Okay, for example, if we set the proper drag reduction the components, the drag reduction rate can be low down as much as 17 to 48%. We can also find the resistance reduction mechanism of the convex structure. Okay, this is a convex structure. Please pay attention to the left picture. Okay, please, the arc surface have been changed. Arc surface a little bit convex. Okay, and the inner surface is a little bit concave. Okay, so through the change of the shape of the T.junction, we can reduce the resistance remarkably. Okay. Finally, the part three. Let me have a look about the low loss components. Here are some presentations of low loss components, the optimized. Okay, the T-shaped shaft, the T.junction, and the cross shaft, the rectangular, like Y-shaped, the T.junction, the Z-shaped, the rectangular section. The rectangular duct portion combined with the T.junction, with the rectified T.junction, and the nutty, the rectangular rectified airballs, and the pie-shaped, or 180, the rectified airballs, and the road-resistant square expansion, the components. Here is the optimized components for HVAC systems. Okay, for the outlets, for the T.junctions, for the way, the different, the different types of the T.junctions. Here is the picture of the pictures of our experimental studies. Okay, from here you can see a lot of the pictures, a lot of the examples, a lot of the research have been done for the T.junctions, for the airballs, for the different for different diffusers and the different the valves. Okay. Here is our team's related articles. Our team's publications about the drag reduction over the 20 years. We are focused on the airballs, T.junctions, diffusers, valves, and so on. Okay, finally, summary. As a very important part of the building energy consumption, the drag reduction of the heating, ventilation, and the air conditioning system should be paid more attention. The local resistance of key components of the heating, ventilation, and air conditioning systems can be reduced by more than 10% by the optimization. The current optimization method merely focused on the air ducts or air pipes of the heating, ventilation, and air conditioning systems. Further research will be aimed at the drag reduction of the water carrier piping systems. The narrow method has been proposed in reduced resistance and energy consumption for heating, ventilation, and air conditioning systems. Okay. Okay, that's all of my presentation. We just introduced our team's research work over the 20 years. Okay. Any problems or questions are welcome. Thank you.
Thank you very much, Professor Li. Very, very comprehensive lecture. Thank you. Do you have any questions for Professor Li, please? Any questions, colleagues? Any comments or questions? Well, I'll just ask a question. All this data you collected, a huge amount of data. Have you included these in any standard like ASHRAE or other national standard for designing a duct system? Have all this information incorporated in any handbooks or standards?
Yeah, thank you, Safa. Thank you for your question. Okay. You know, as I mentioned, you know, our teams have done this research over 20 years. You know, some findings have been, you know, some findings have put into the, you know, the handbook, such as the industrial design handbook. Okay, this book is edited by the Goodfellow, the Professor Goodfellow, in Canada. And some of the findings have been incorporated into the heating, ventilation, air conditioning design book. Okay, but I hope, okay, these findings can be used, okay, more widely, okay, can be into the, you know, the different books or textbooks or different books or the booklet. Okay, I hope, you know, this, you know, the long-term research can be useful, can be helpful for the, not for the, you know, the Chinese people, not only for the Chinese people, also can be helpful for the world. Okay, thank you.
Thank you. Any other questions, colleagues? Any questions?